Okay. We're getting down to the end. For only 4 lessons left. I've reviewed all of test 2 for partial credit, except in the case of if anyone was given an extension due to the due to the storm. I'll check on that and make sure that they're all reviewed for partial credit as well. Um, and the average, let me check. After giving partial credit, it was fairly high. Um, the average was at 82. The median, which might be a more reliable indicator, was a 86. Yeah. Now, if test 1 and or test 2 did not go so well for you, keep in mind that the final exam will replace the lowest test if it'll help your grade. So in other words, it's not the lowest test itself. Also, I sent a message about this, but because of so many having issues due to Hurricane Zeta and such, like some are still without power or internet, I've just done away with late penalties. So this is something that anyone could take advantage of. So that also means that if you have old lessons that were that you did not complete, you have the opportunity to boost your grade a bit by going back and doing those. So over the next 2 weeks, we'll be finishing off a new material. I'll spend some time after that reviewing for a final, and then that'll be it. Okay. So we'll get going on this lesson, new chapter on logarithmic and exponential functions. Okay. Today it'll be about logarithmic functions. So the function we'll be working with is ln of x, known as the natural log of x. And here's the definition of a logarithmic function right here. So if y is equal to the natural log of x, that is equivalent to saying that e to the y is equal to x. So y, the logarithm serves as an exponent. The number you're taking the natural log of is the result of exponentiating. And we call it the natural logarithmic function because the base is this number e, also known as Euler's constant, and that's the base of the natural exponential function. E is a particularly important number throughout mathematics, just like pi, for instance, that has a lot of applications in differential equations and so forth. So that's why it's being featured so prominently here. There are other logarithmic functions that are often used. For example, logarithm to base 10. That's used to define the Richter scale for earthquake intensity. Also, a logarithm to base 2 is sometimes useful, but they all relate to this natural one. Now, in this lesson, we'll be dealing a lot with taking the natural log of certain functions, and often it's helpful to rewrite a function so that whatever you have to do, such as taking a derivative, will be easier. So these properties, these three right here, are going to come up a number of times. So if we're taking the natural log of a product, that's the same as the sum of the logs taken individually. So log of a product is the sum of the logs. Similarly, the log of a quotient is the difference of the logs. And finally, natural log of exponentiation, you can take the exponent and pull it down. So natural log of a to the b power is b times the natural log of a. So we'll be using these throughout. All of these relate to laws of exponents that you're familiar with. So like this one comes from a fact that if you have x to the a, x to the b times x to the b, that's the same as x to the a plus b. So it's the same idea. It's just reversed. Now, in all these problems, we need to take a derivative of some function based on the natural log. And so here are the differentiation rules here. So if you just have plain old natural log of x, the derivative of that is 1 over x, or x to the minus 1. So then if you take this rule and combine it with the chain rule, that's for the natural log of some function of x instead of just plain x. So notice here, when you take a derivative of ln x, you get 1 over x. So here we're also going to get 1 over g of x. But because of a chain rule, you have to multiply that by the derivative of what you're taking the log of, and that's why we have as g prime in the denominator. So whenever you see a function like this, natural log of something, and you have to take a derivative, then the derivative goes up top, the function itself goes down below. Okay, so this is a type of problem that you've seen before, finding the absolute max and min of a function on an interval. We're going to follow the same procedure where you take the derivative, set it equal to 0, and also check the endpoints of the interval you're given, because those are your candidates for max or min. The only difference is we're applying this procedure to this kind of function that involves the natural log. So we're going to take the derivative. I'll just repeat, these are the rules that we'll be using. So the derivative, f prime, you look at what you're taking the log of, 3x squared minus 12x minus 12, that function as is goes to the denominator. And then the derivative of that is what goes in the numerator. So that's how we get the 6x minus 12. It is possible to simplify this because every coefficient that we see here in this function, both above and below, is divisible by 3. See, some answers in Hawks do that. That's something to keep in mind. Although it's not absolutely necessary. For instance, the simplification was not done here. All right. So now we need to find out where this is equal to 0. So if we go ahead and set this equal to 0, simply setting the numerator equal to 0. So we just really need to solve 6x minus 12 is equal to 0. So we go ahead and solve this. We have 6x is 12, therefore x is 2. The problem is, and this is something that came up on a test, by the way, there were problems there where you had to find the absolute max and min on some interval. So you go ahead, take a derivative, set it to 0, you find a critical value, and it turns out to not be in this interval. If it's not in the interval, you can't consider it. We're only looking at x values between here and here. So in this case, we got one critical value where a derivative is 0, that's x equal to 2. Because it does not fall within this range, we ignore it. It is not a candidate for the absolute max or min. So something to keep in mind for the final, where problems like this may come up. Make sure you're only considering x values that fall within the interval that you're given. So in this case, the only candidates we have are the two endpoints. So we're just going to take these values and substitute them into the original function. And when we do that, so we just go ahead and plug and chug here, and we get this value, 5.21, and then 6.35. Now, because answers are to be rounded to 2 decimal places, so that's what I've done here. So now we see that this value is the smaller of the 2. So that's where the absolute minimum occurs at x equals 10.3. The other value, therefore, the larger has to be the absolute max. So we have for the absolute minimum, notice here with the directions, write your answers in the form x f of x. So if they want an ordered pair of an x value and a y value. I noticed also in a test that often the answers were not given in the form that Hawks required, and that's why it marked you wrong. So when possible, if I could tell that you had the right values, then at least I was able to give you credit. But that's something to keep in mind. Okay. So since 10.3 is where the minimum occurs, the y value is the other part of the ordered pair that you enter in the answer box for absolute minimum. And then for absolute maximum, the x value is 16.1. This is a y value that is included in this ordered pair. So these 2 ordered pairs are your final answers. Any questions about dealing with this logarithmic function? So in fact, this whole lesson, there's a lot of problems getting practice on taking derivatives of functions like these. Now, we could just go ahead and use the differentiation rules that either you knew before or the ones that I just gave you. But before we start, it's actually a good idea to rewrite the function so that whatever you're taking the natural log of is as simple as possible. So that makes things easier down the road. So this property that I mentioned earlier, log of a to the b is b ln a, is helpful here because that means I can just take this exponent 4 and pull it out. So now this is my function. So now so the derivative will have a simpler form here. So for first term, just use a familiar power rule, and then we have minus 4 times the derivative of the natural log function, which is 1 over x, and that's what gives us this term here. If you had left it as is, which you could do, then you would have to do what you would get is the derivative up top, 4x cubed, and then divided by x to the 4th, which would also simplify to this. But if you have a logarithm expression that's raised to an exponent or something in here that's being multiplied or divided, it's a good idea to use these properties just to simplify things later. Now, if it's next one, in addition to the rules that I showed you for taking a derivative of a logarithmic function, what other differentiation rule do we need to handle this?
Product rule.
Yes, this is a product. So we need to work with these 2 functions, 17x to the 4th and ln of x to the 4th. So as I did way back then in that lesson on the product rule, you get your ducks in a row. So your 2 pieces are 17x to the 4th and ln of x to the 4th, which is then rewritten like in the previous problem. So that'd be 4 ln x. So the f of x is equal to p times q. Now, to apply the product rule, you need the derivatives of these two pieces, and that's what's done over here. So power rule for this one, and then just the rule for derivative of ln of x used here, again, like in the last problem. Once you have your ducks in a row, you can just put these four pieces together. So we have q times p prime. So these two, the two in the middle, are multiplied here, and then the two on the outside are multiplied here. Now, in the second term, we have x to the fourth up top and x down below, so certainly that can be simplified. And then 17 times 4 is 68, so this is the answer that results. I rearranged this. When you have natural log of something times another function, it's just customary to put this on the left just because it's less chance of misinterpreting it. So we have here the natural log of only x to the fourth is being taken. This is not part of that. Here we have another function on an interval, and the idea is to find the absolute max and min, just like in the first problem, rounds to decimal places. And again, the answers need to be in an ordered pair, x value and the y value that goes with it. So here too, I'm going to use properties of logs to rewrite the function because I have natural log of x squared. So the 2 can come out. So ln of x squared is the same as 2 ln of x. And then I just clean it up here. So this is a function that we'll be working with now. So we get this power rule for this, and then 20 times derivative of natural log of x is just 1 over x. So now we need to set this equal to 0 to find critical values. Okay, so we take that derivative from before, set it to 0, and then just do some rearranging. We want to get x by itself. So I'm going to multiply both sides by x to get that one out from under here. And then the 21 will be moved to the other side also. So this is what we have. So then we take the cube root of both sides. Equivalently, we're raising both sides to the 1/3 power. So x is going to be 20 over 21 to the 1/3 power, but rounded to two decimal places, that's 0.98. So this is the one and only critical value we have. Now remember, when you get this, however many critical values you have, check them. Do they fall within the interval? In this case, it does, whereas in the first problem, it did not. So that is a candidate for the absolute max or min. So now we have three candidates. We have a one critical value of 0.98, and then these two endpoints, 0.71 and 48. So now we just need to substitute all three into the original function. Okay, so 0.71, 0.98, and then 48, and to see what we get, see what your calculator gives you. So we see that the smallest value is this one right here at the critical point, 0.98. So a function starts at a little higher, dips a little bit, and then it really takes off. So at x equals 48, it's this ridiculously large number here. So this one represents the absolute minimum on the interval, and this one, the absolute max. So those are the two ordered pairs, absolute min and absolute max, that get entered into Hawks. Any questions about that one? Okay. First word problem. You're given this profit function. It's now logarithmic. I mean, you've done this kind of problem before, just not with this kind of function. And remember, when it's marginal, that's code for taking the derivative. So that's all we're going to do here is take a derivative of this given profit function. So we have 44 for the first term, and then for the second term, we have ln of a function. So it's the derivative of this divided by the function itself. So we have 6x cubed plus 4 goes down to the denominator. Then take its derivative, so 18x squared, and that's what goes in the numerator. Just to match the answer that Hawks had for this problem, and this is not absolutely necessary, that every coefficient here can be divided by 2 above and below, so I just went ahead and did that. Sometimes Hawks may flag an answer as, instead of simply saying correct or incorrect, it may label it as unsimplified. So for example, if your answer is a fraction and you did not reduce it to lowest terms, then it calls it unsimplified. Now, keep in mind for tests, I've configured Hawks to give full credit when it's an unsimplified answer. And that's it. That's all that's required in this problem, is just to get the derivative. Next application problem, we have number of units sold as a function of X, which refers to thousands of dollars spent on advertising. The natural log function is a function that it grows as X increases, but it grows pretty slowly. So the way to interpret it says, if you spend more on advertising, then you will sell more furniture, but there's a diminishing returns effect. That as you spend more and more on advertising, the amount of number of sales you get from that extra advertising diminishes. Okay. So first question: how much is sold? If you spend 7,000 on advertising, and both cases we're going to round to the nearest whole number. Now X, pay attention to units here. X is thousands of dollars spent on advertising. So X is just going to be 7. So that's what we'll substitute into this function here. So we just have your calculator work that out, and after rounding, 296 pieces of furniture are sold. Then what you want to find out is, so what's the rate of change if when you're spending that much on advertising? And this will give you an idea. Like if you spend $1,000 more on advertising, how many more units can you expect to get to sell? So that would be n prime of 7, because rate of change, remember, that refers to derivative. I saw a number of cases on the test where, like for instance, a problem asked for a second derivative, and someone would give a first derivative. So little things like that, and that's a case where I can give partial credit at least if that is done correctly. But for a lot of times, where the wrong function was provided or the wrong function used. So first we need the derivative of this function. So a 210 will not give us anything, so we're just focusing on this part. And here we have log of a function. So whatever function you're taking a log of, that goes in denominator, and then its derivative is in the numerator. So that's where the 3.5 comes from. And then we just go ahead and multiply this out. So this is the derivative. So now you can just substitute x equals 7 into that, and you get a decimal. It's like 3.3 something, but we're rounding to the nearest integer, so it turns out to be 3. So what this is saying is, if you once you're spending $7,000 on advertising, for every additional $1,000 spent, or if you're going to bump your spending up to 8,000 from 7,000, then you expect to sell only 3 more pieces of furniture. So you're not gaining much more from additional spending. So then you have to decide if it's worthwhile. And the thing is, if you go beyond 8,000 and spend even more, because this derivative, as x increases, the derivative will get smaller and smaller. So you'd actually be gaining even less. So right now, you're going from 7,000 to 8,000. That means you're boosting your advertising spending by about 14%. That's sort of 1/7. But then you're only selling 1% more furniture. So it's definitely something that should give you pause. Okay, here all this asks for this next one is just finite derivative. Now, one thing to be very careful about is look at the way this is written. So we have ln of x, the whole thing's in parentheses, and that is cubed. I want to contrast this with like something from a previous problem, like ln of x squared. Notice the square is inside the parentheses here of what you're taking the log of. So these two functions are very different. Because so this is not one that you can apply that nice property of logs to, where you can take an exponent and pull it down. So if this was log of x cubed, then you could, and this 3 would not be written here, it'd be inside here. So pay attention to where the exponent falls within the parentheses following log. It does not in this case. So go ahead and take the derivative. So we're using a power rule here, a general power rule. So 3 comes down, and then you have natural log of x, the whole thing squared, and then you take the derivative of ln of x, which is 1 over x. So then you can simplify all of that. So same thing applies here. See how they're written differently. And yes, they have something in common, but the placement of a 2 is different. So be sure to pay attention to this distinction. So this one I could rewrite as 2 natural log of x. Can't do that here. The key is whether you raise to a power before or after you take the log. Here it's before, here it's after. Okay, here the goal is again to take a derivative, so this is a situation where you can use one of those nice properties, because notice we have something being raised to the 5th power, and then you take the log of it. So I can just take this exponent of 5 and pull it out, and now I have this. So now I have a simpler function to take the derivative of. So this function here, we're taking a log of, that goes in the denominator. And then take its derivative, and that's what goes in the numerator. So that's where this 8x minus 60x squared comes from. Then, at least, again, not essential, but just to match what was the final answer is given in Hawks, see what you can factor out. So, for example, in the numerator here, it's possible to factor out a 4x. And in the denominator, it's also possible to factor out a 4x. So after factoring out 4x here and here, if those cancel, then this is what we're left with. And then I just take the 5 and distribute that through the numerator, and that gives the final result here. Okay. Two more problems that both involve just taking a derivative of some nasty function involving natural log. Here we have the same thing. Now, you might think, oh, we have a quotient involved here, therefore it's going to be necessary to use the quotient rule. But it turns out it's not. So I'm going to use the same property involving the exponent. I can take the 2 and pull it out. But I can also use this property. The log of a quotient is the difference of the logs. So that's what I show here. I take the exponent and pull it out. And now I have a log of its quotient. But then I rewrite the log of its quotient as a difference of a log. So log of a numerator minus log of a denominator. Now I can take the derivative of this. So in both cases, in both these terms, I need to use that rule for handling a derivative of logarithmic functions where I have a derivative over a function itself. So what does that give me? So I have a 2 just sitting out here. So the derivative of this part is just going to be that function goes down below, and then its derivative goes up top, and then minus 2 times the same thing happening here. This function goes in the denominator. Its derivative goes in the numerator. And then after that, it is possible to do some simplifying. For example, in this fraction here, every coefficient is divisible by 11. So I cancel an 11 above and below. So I have 3x squared over 2 plus x cubed. And then I got to multiply by 2. And that's what gives me this 6x squared. Here, none of the coefficients, there's no factor that's common to all 4 coefficients. So the only thing I could do is just take this 2 and distribute it through the numerator. So that's the only thing I can do for coefficients. There is at least one factor of x above and below, so I can factor an x out of a top and out of a bottom. And that's why you see here, notice every x, the exponent is 1 less than what it was. That's just from factoring out what you can. And even though the simplifying is not absolutely necessary, if you're working these problems like in practice or certify, and you get it wrong, and they show you what the correct answer is, it may be difficult to distinguish your answer from a correct answer if since they simplify and if you don't. That's why I'm telling you how they go about simplifying their answers. So at least when you're practicing, you can see, like if you go ahead and simplify the same way they do, then chances are, if you're using a right approach, that your answers will be almost the same, and you can see what term you got wrong. Okay. Last one, natural log of this monstrosity. But once again, we can use the properties of natural log to simplify this considerably before taking a derivative. So we'll use this property again because of a cubed. And also the log of a product is the sum of the logs. So what happens here is, here we have log of a product. So I could say natural log of this with the cube included plus natural log of this. But then once I've taken the log of this cube, I can use this property to move the 3 out front. So this is what we have. So this is the same as a log of 9x cubed plus 22x squared, the whole thing cubed. But I've written it here since that's easier for taking a derivative. So now use that same rule for differentiating logarithmic functions. So here, this function we're taking a log of, that goes in the denominator. Its derivative goes in the numerator. And the same thing over here. Function goes down below, derivative goes up top. Here, there's nothing you can do with the coefficients to simplify, because like these coefficients are a common factor of 3, but these don't have a factor of 3. There is an x that you can cancel throughout. So you factor an x out of here and out of here, you can cancel them. And also this 3 needs to be distributed through the numerator. So this is how we get the final result. So 3 distributed through here, and then an x is canceled above and below. Now we come to the end of a lesson. Are there questions about any of these? Okay, I will stop recording at this point.